And so in this chapter dealing with moles, we look at a variety of different concepts involving moles. So the beginning, it talks about what a mole is, and then we use moles. We use the molar mass to go between mass and moles. And that's a very common calculation we do in general chemistry, is calculating moles from mass by using the molar mass. And then it also discusses how to, if we have the moles, how to calculate the number of entities, which is through Avogadro's number, like the number of atoms or molecules or formula units in a given number of moles. And then it delves into calculating the empirical and molecular formulas from empirical data. So just before we start this problem, just to give a little refresh on what empirical and molecular formulas are. So empirical formulas they show the smallest whole number ratio of atoms or ions in the formula. So whenever you look at the formula, if the lowest, if the common multiple is 1, it's the empirical formula. And that's how you can know if something is an empirical formula. If you look in the common multiple between them, that's the empirical formula. And typically, ionic compounds are written as empirical formulas. So that's empirical formula. Now, molecular formula is a little bit different. Shows the actual number of atoms in the compound or in the molecule. So it's not the lowest whole number ratio of 1, it can be any ratio. And so sometimes the molecular formula does equal the empirical formula. Sometimes. So to give you an example of the difference between the two, we'll start with something like hydrogen peroxide. Its empirical formula is HO. So you'll notice the whole number ratio between the atoms is 1. However, its molecular formula is H2O2. So you see the difference. Now we're showing you the actual number of atoms in the formula. And so it's just one step to go from empirical formula to molecular formula when we work these problems. And we'll explain that step when we work through the problem as well. Another example is ethene, which the empirical formula is CH2. But the molecular formula, C2H4. So again, you see that the actual number of atoms can or have a different common multiple than the when we have show the lowest common multiple of atoms. Now, compounds can have the same empirical and molecular formula. For example, if we look at propane, empirical formula is C3H8. Its molecular formula is C3H8. So sometimes that can happen as well. Especially with covalent compounds, the empirical formula can equal the molecular formula. So we're going to go through the steps to determine the molecular formula for these different compounds. So that's what we're going to be working on now. I just wanted to give a little refresher on the difference between the different types of formulas. And so when we're dealing with or calculating molecular and empirical formulas, typically there's been an analysis on the compound to determine either the mass of each element in the sample or the percent of each element in the sample. And so in this case, this compound was analyzed and it tells us the percents of carbon, hydrogen, nitrogen, and oxygen in this compound. Now there are different ways you can approach solving for the molecular formula. If you do it a different way and you get the same answer, no problem. But for us, what we're going to do is first calculate the empirical formula, and from the empirical formula, we can calculate the molecular formula. One thing to note is the way that it's written in the problem, the elements, is the order you have to write the formula. And so since it's given us carbon, hydrogen, nitrogen, and oxygen, when we write the formula, we're going to write carbon, hydrogen, nitrogen, and oxygen. So now let's get started and determine the molecular formula of this compound. So this molar mass in parentheses is the molar mass of the molecular formula. So that's always given to you in the problem. So this is of the molecular formula. What we're going to do is, in order to determine the molecular formula is equal to some number n times the empirical formula. And so this is what you need in order to determine the molecular formula. You need n and you need the empirical formula. And so n is a ratio between the molar mass of the molecular formula, I'll use MF, divided by the molar mass of the empirical formula, EF. So once we know the ratio of the molar masses between the molecular and empirical formula, we can find n. Right now we can't find n because we don't know the empirical formula. So the first thing we need to do is to determine the empirical formula so that we can calculate its molar mass. And then once we know the molar mass of the empirical formula, we can find this n value and then multiply the empirical formula by that number. And most of the time, this n is an integer, but sometimes it could be decimal. So the first thing we need to do is, since it's given us percents, we need to assume 100-gram sample. And the reason we assume 100-gram sample is because it's very easy to take the percent of 100. And so now we get the mass of each element. So we have 19.8 grams of carbon, 2.50 grams of hydrogen, 11.6 grams of nitrogen, and 66.1 grams of oxygen. And so this is the first step. We assume 100-gram sample and we can find the mass of each element. The second step is to find the moles of each element. And so for carbon, you take the mass divided by the molar mass of carbon, which is 12. You can use 12 or you can use 12.01, it's fine. And then we take hydrogen, the mass divided by its molar mass. You can use 1 if you like. And again, I'm getting the molar masses from the periodic table. It's the number below the element symbol, the decimal number that you see. For nitrogen, 11.6 divided by 14. And one more, oxygen, 66.1 divided by 16. So now we can determine the moles of each. So mass divided by molar mass gives us moles. We get 1.65, 2.5, get 0.8286, and 4.13. So now we have the moles of each element. The third step, divide the moles of each element by the smallest number of moles. So you look at your different moles, you see which one is the smallest. We're going to divide everything else by that. And so when you look at the moles, you see nitrogen is the smallest. So then for carbon, it's going to be 1.65 divided by 0.8286. Now, one thing you need to remember is try not to round too much in each of these steps, because the more you round, it's going to cause your answer to err. So I would always recommend 3, 4, or 5 significant figures in each step as you move through it. So for hydrogen, 2.50. Nitrogen, and oxygen. So we get approximately 2 for the first one. The third, the hydrogen's like 3.017. You can just round that to 3. That's close enough for 3. And the oxygen is 4.98. That's close enough to 5. And so you notice here that the ratio are all whole numbers. Since the ratio is all whole numbers, then we can go ahead and write the empirical formula. So the empirical formula would be C2H3N O5. And then we calculate its molar mass. So 2 times 12, 3 times 1. And this will give us the molar mass of the empirical formula. And we get 121 grams per mole. So now we'll calculate N. So N is the ratio between the molar masses. So the molar mass of the molecular formula is 120. The molar mass of the empirical formula is 121. And it's approximately 1.99. So in this case, the empirical formula is the same as the molecular formula because your N is 1. So here we have a compound that contains sodium, carbon, hydrogen, oxygen, and nitrogen. What's its molecular formula? If the molar mass is about 169 grams. So it should be an S here. So we've done some analysis on this compound. It gives us the percents of each element in the compound, and it tells us The mass of the molecular formula is 169. So again, what this means is that this is the molar mass of the molecular formula. So the first step, since it gives us percents, is to assume a 100-gram sample. So if we assume a 100-gram sample, we can find the mass of each element. So now we know the mass of each element. The second step is to find the moles of each element. Again, mass divided by molar mass gives us the moles. Again, the molar mass comes from the periodic table. We get 2.95. So here we've got the moles of each element. The next step is to get the ratio by dividing all the moles by the smallest number of moles. We're doing this so we can get the ratio. So the smallest is sodium. Now the moles of nitrogen are very close to the moles of sodium, so that's going to be approximately the same ratio. And so here the ratios are all whole numbers, so we can write the empirical formula. And now we can determine the molar mass of the empirical formula. And again, we get 169 grams per mole. So here again, the empirical formula equals the molecular formula. So here we have an amino acid, contains carbon, hydrogen, oxygen, and nitrogen, along with sulfur. What's the molecular formula? The molar mass is approximately 121. So again, this 121 is the molar mass of the molecular formula. And so in our first step, we're going to assume a 100-gram sample. So now we can get the mass of each element. So now we know the grams of each element. We're going to find the moles of each element. And so you notice here that nitrogen and sulfur have the smallest number of moles. So we're going to divide everything by the smallest number of moles to get the ratio. And so you see here that we have whole numbers. We're very close to whole numbers, so we can go ahead and write the empirical formula. Then we can find its molar mass. I got a bad luck at picking out these problems. So we have a molar mass of 121. So in this case, N is 121 is 1. So therefore, the empirical formula is the same as the molecular formula. So here we have our last problem. We have a carcinogen with a molar mass of 252.3, contains 95.21% carbon and 4.79% hydrogen. What is the molecular formula of this compound? So again, we're going to assume a 100-gram sample. If we assume a 100-gram sample, we have the mass of carbon and the mass of hydrogen. So then we find the moles of each element. And we get 7.93. So we're going to divide by the smaller number of moles to get the ratio. So here, hydrogen's a smaller number of moles. And here you see, in this case, we get a ratio of 1.66 to 1. Because when you take 7.93 divided by 4.79, it comes back to you as 1.6555. So we'll round it to 1.66. Now you can't round this to 2. It's too far from 2 to round. So whenever you have a decimal like this, you have to multiply it by something to get rid of the decimal. For example, if it was a half, you would multiply by 2. If it was a quarter, you would multiply by 4. Here it's 2/3. So we would multiply by 3. But you have to multiply both of them by 3. And so when we do that, this becomes 5. Because this is 1 2/3. When you multiply by 3, you get 5. Now this is the whole number. Now you have to make sure that you multiply all the elements by whatever you're multiplying the element that's not the whole number. Because everything has to be multiplied by 3. So what this is telling you, a ratio of 1 to 1.6 is the same as a ratio of 3 to 5. So these are whole numbers now, so we can write the empirical formula, which is going to be C5H3. We get the molar mass. (63 grams per mole). Now we can find N. And we get a factor of 4. So what this means is we have to multiply the empirical formula by 4 to get the molecular formula. So you do 4 times C5H3, we get C20H12. So that's the molecular formula of this carcinogen. So again, the same process. Since it gives us percents, we assume 100-gram sample. We find the mass, then find the moles of each element, divide by the smallest number to get the ratio. Since the ratios weren't whole numbers, we had to multiply by something to get rid of the whole numbers. Once we found the empirical formula, we determined its molar mass. We found the value for N. Then we multiply the empirical formula by N to get the molecular formula.